In the beginning, I will show some of the best pictures I managed to convert, or just like good examples, how it can look. This is one of them. It's on normal 8-bit Atari. As you will see later, some of those pictures use flickering, like switching to images. So on some display they may not look as good as here, but on LCDs or projectors they look really good. I will address each of the problems individually. So I will also show you some of these pictures on the real Atari, because the projector really isn't very good. Clearly, this looks kind of bad. So the approach, which I called new for the title, is not really anything new. It's just old ideas put together, and there are some main tricks how to achieve it. One is PAL mixing, which is in PAL, two lines are always averaged together. I will have some special sheet for this. So you can combine color from one line with brightness, which is on next line. This has been used on Atari for ages, and it's certainly nothing new. Flickering, like using two frames, quickly changing, basically in 25 Hertz, is also used on basically all platforms to create more colors or to increase resolution. There are always some techniques how to improve how much it seems to be flickering. There are some modes which are really bad and impossible to watch. On the other hand, the modern LCD screens typically merge the consecutive frames together, so you can really change between black and white screen and it won't be flickering at all. But we still wanna support CRT screens, so I think I found some ideas how to improve it. Third point is dithering, which is really old technique how to get more colors with few colors. 4 is like, maybe I will come with something more, and I will address individual point now. So the PAL mixing, it's not really well visible, but if I zoom even more in, you can see that without PAL mixing there is dark red line and gray line, and another dark red line and gray line. This is how the picture is really generated. This is how it will look in emulators, unless you turn this specific features on. Most emulators can do it because a lot of demos and software on Atari uses it. It's really old technique. But typically on Atari this has been used with modes which have 80 pixels resolution, which is pretty low for pretty much everything, especially for things like faces and photos, so that's why I didn't like it. Anyway, the base of the technique is the same, and if you look on the right side where the PAL mixing is turned on, you can see that where here is gray, here is yellow, because the color is taken from the previous line. This is feature of PAL, which was originally created to better remove effects which were introduced by reflections of the TV signal, because the color information on both PAL and NTSC is coded into phase of the color signal, so any time differences can shift the colors. And PAL, as the newer norm, introduced this mechanism that odd and even lines use opposite phase of the color information, and they average the two lines together just for the color information. So any error introduced by reflections is perfectly cancelled and you get the original color, and it's very absolutely unintentionally very useful feature for mixing color from two lines. So what you see here is basically I will get to it later. But you can see that this is how the picture will look if you don't have the feature on. There is also a problem that, for example, if you use WebXE with RGB monitor, you will not get PAL mixing because this is not how the picture really looks. It's just how the old TV will interpret it. Generally, high frequency modulated image does it every time. Basically, all TVs do it. Also, the composite video typically works okay, and with S-video it sometimes works, sometimes not. It depends on the TV. We have TVs. I would say most of the TVs will display S-video like this. They will just think, oh, it's S-video. There is no information. The color is not encoded in the face, so I just don't have to worry about it. Maybe this. But generally, there is no norm for this. It just depends how the manufacturer of the TV, what was easier for them generally. So you can never know. Which is one of the problem of those formats, because typically, if you create a software, you want it to look same. Doesn't matter what hardware you use. This is not the case, so it can look bad on some displays, but generally it's okay. It's effect which have been really used on Atari for ages in many demos. So if you have emulator which doesn't support it, it's wrong emulator, definitely. So this is first feature. So the mode, that's why the mode looks so like there are bright lines and dark lines, because the dark lines are the lines with the color, and there is on the darkest possible shade on Atari just color information. So there is darkest red, darkest blue, darkest green, colors like that. And the bright ones are originally gray. So there are several shades of gray color without any color, and PAL mixing will put them together. So basically I'm getting more color depth than I would normally have. Another trick is to use two consecutive frames flickered in 25 Hz to get more colors and more shades. This is one of my simplest modes. I will show the modes later. So in my simplest modes, I used 4 colors on the color lines: red, green, blue, and yellow. And if I flicker them, I can get color between them. So if I flicker red and blue, I get purple. So basically 4 colors, which I can flicker all combinations. Red and these combinations typically don't make sense because that is just the combinations on the border make sense. So if I start with 4 colors, by flickering I get 8 colors. With shades, I only flicker the neighboring shades. So if I start with 4 shades, I will get 7 shades in the end. And that's the basic of my of these modes, I use 4 colors graphics modes. Typically, the final resolution is 160 per 100 pixels, and the pixels are square, which is very important for images like this. And there are, I will get to limitations later, but basically that's the idea. The old modes typically used lower resolution and more colors, typically 16 colors and 16 shades, which is perfect, which is really, it can give you 256 colors, which is perfect, but the resolution was really bad, so I didn't like it. So next step is dithering. Dithering is method how to get what looks like more colors, even if you don't have more colors. This is typical, I very like Floyd-Steinberg dithering, which looks like this. This is just black and white, but it looks like more shades of gray, even if it's just black and white. I use this technique a lot, except I modify it somewhat. The classical Floyd-Steinberg dithering works, you encode the image from top to bottom, and basically at every point you compute how the error of the current image. So if you want to make like 50% gray and you only used so far black pixels, it will gradually increase the error, and at some point the algorithm will say there is too much gray and the error is big enough, so we can put one white pixel there to make it better. Basically, it estimates in every position, is it better to have black pixel here or white pixel here? And that's also why this method is called error distribution, because it computes the error and tries to fix it. The original Floyd-Steinberg algorithm uses 3 pixels. This is pixel which is computed at the moment, and it uses 3 pixels from before and 1 from below or from top, depends on from which side you are encoding the image, and 1 pixel from right. So it only uses 4 neighboring pixels and creates new pixel. This is very useful if you want to encode the picture in one pass. If you are just getting pixels one by one and want to convert it one by one. But it creates some ugly artifacts like things here that you see, like rather regular diagonal lines. It's very typical artifact, and it's all based on the fact that only 4 pixels are used for estimating the errors, only the pixels which already were converted. And I don't do it like this. I use a method which is not in one pass. I basically convert the image once. I will show you later how it looks. And that I just find the closest color, and then I find random pixel in the image. I use all neighboring pixels or 8 to estimate the error, and then I decide what color to put in the middle to improve the error. So it's not one pass, it takes some time. It's almost, you could almost say it's brute force approach, because the error, basically the global error of the image is improved over time, and I typically do like 10 times number of pixels of iterations. So I recompute all the image 10 times, and it mostly stabilizes, and the image it doesn't change much after that. So it's also similar to solving solution of large matrices. It's basically gradually improving the image and finding better combination of pixels to get the closest possible solution. There is also other very commonly used method of dithering, which is called ordered, also Bayer dithering, which just use regular pattern to gradually come from one color to another. It sometimes look good, sometimes not, because there are also some regular patterns which may look bad. On the other hand, the 50% combination is regular checkerboard, which looks really good, while in Floyd-Steinberg the 50% is mostly random dots and it can look really bad. So in some situations this dithering is better, but it has one big disadvantage compared to Floyd-Steinberg. It can be only used basically to go from one color to another, and it's very useful if the colors, like the amount of red colors, amount of green, amount of blue, if it's same. It's been also used famously in Windows, where it does very nice use of 16 colors, but my system basically uses random palette that I have red, green, blue, yellow, and even my brightnesses are not perfectly same distance, and this ordered dithering is not very good for random palettes, while Floyd-Steinberg can just take any colors, any number, and find the best solution. Anyway, my method, I will show you later, can somewhat combine both these dithering algorithms. Basically, I can do some bias in the Floyd-Steinberg. I can say if you are on even pixels, treat them as darker, and if you are on odd, treat them as brighter. So if you get, for example, the 50% gray, and he has somehow arranged same amount of black and white pixels, I can tell it, okay, if you are not sure if to use black or white pixel, just follow these patterns. So the methods can somewhat be combined, and for some pictures it's useful. So here are the main variations of the image, of the types I use. The most simple is 4x4. It means I use 4 colors and 4 brightnesses. So basically there is just one screen mode on Atari. I don't know the numbers, sorry, but it's just the classical color mode with 160 pixels per line and with 200 lines. And there is a kernel routine which switches the colors on every line. I have to switch 4 colors, so which is perfectly okay if you use graphical mode. It's not so good in textual mode. In textual modes, it's really on the border what Atari can do. Anyway, it's nothing special, so it gives me basically 16 colors, and I have to take the image, use dithering algorithms to convert it to these 16 colors, and then I have to encode the 16 colors. So brightness is in one line, color is in other line, and that's all. I will show you later all the comparison of how the pictures get improved as I add more colors. More complex, and basically one of my newest addition is mode with 4x6, which uses the same 4 colors but uses 6 different brightnesses. And how to make 6 brightnesses when Atari can only do 4? Well, it can do 5 if you're using text mode, because you can use inversion of the character to give you another color. And if you are working with per character basis, which you are, if you are using inversion, you can also get another color with PNG. because on Atari you can use PNG predicted to maximal size, and it will just perfectly, each pixel will cover one character. So you can look at it like on every character I can use 4 brightnesses, but I can choose which 4 of the 6 brightnesses it is. So basically there is something like attribute map or color map on C64, where for every character I say it's the dark character, it's the medium character, or it's the bright character. And then I use just field data to encode the information. So there is some limitation. I can use white and black in one character, but on most pictures it's not a problem. These 2 modes, the first 2, they don't use flickering. So they look perfectly static, even on CRTs. But 16 color is not much. The other mode creates 4x6, which is 24, which is better, but nothing special. The flickering modes really bring the color count up. So this next mode is basically this one with flickering. Because I use, how I showed here, 4 colors by using flickering give me 8 colors, and 4 shades of gray by flickering give me 7 shades of gray. So that's why the colors and shades are multiplied differently if I use flickering. So that's why I have 8x7, and it's 56, which is of course way more than 16 or 24. So the image really looks better, but it flickers a bit. Anyway, the flickering, if I only use flickering of 2 colors which are neighboring, so let's say brightness 14 and brightness 10, that's much better than using like black and white. So if you just flicker colors which are already close together, it's not so visible. Also, I use some systems, so the flickering is randomized over the image, and sometimes you can get, especially with ordered flickering, you can get situations where one field, which is one of 2 frames, one field mostly contains brighter pixels, while the second mostly uses dark pixels. So the image is really dark, white, like whole picture on average. But you can either randomly or in some regular system exchange pixels between these 2 fields. So the both fields have on average same brightness, which is another method how to lower the perceived flickering. And I use both of these methods, and it's not so bad. It really depends on displays. Some displays are really bad, but general CRT is okay. Also, some people are really sensitive to it and see it from miles away. Some just don't care, so you will see. And the best method I use is this one, which is basically this one with flickering. So 4 colors give me 8 colors, same system as here, and 6 shades of gray gives me 11 shades of gray. And again, there is limitation that in one character I can only use some of them. So here I will show some. This is the simplest mode with 16 colors, so 4 colors per line, 4 shades of gray per line. You can see that the dithering is really visible, and well, it's okay, it's better than 4 color images on Atari, but it's nothing special. You see the detail in the eye, there's nothing. On the lid, there's nothing. This is the better method, which uses inversion and PNG to achieve 6 different shades of gray. And you can see that the gradation, basically one of the things I found is that create more colors is not so important as creating more shades of gray. That's much more important because it smooths the dithering, and I can always dither some color between using the colors I already have. But getting nice gradation of the brightness is much more complicated. So if you go back and forth, you can see that 6 is a lot more than 4. Some images in this mode already looks quite okay, and this one not so much. It gets a lot better in the next mode. This is the first flickering mode, but this mode has no limitation of characters. I will show what I'm talking about, but if you go back from first, you can see that there is already significant improvement. And this is the last mode. Basically, it smooths the dithering. Basically, everywhere if you see significant dithering, the next mode almost makes it invisible because it already has 11 shades of gray, which is quite a lot. But there are some artifacts, like here you can see it's slightly darker because on every character I can only use some colors. In one character I can use all colors, but on image like this, you can always, it just simply breaks into dark characters, medium brightness characters, and bright characters. So this is one of the few places where it's really visible. On most pictures, it's really hard to find.
May I have a question?
Yes, this is the original image.
Well, now we have a PC, we have a screen, and we have a projector. So how does this all depend on the original device and what it's projected on?
It mostly depends what is the imager. LCD or even the projectors typically use merging of the fields. So 25 Hz will never flicker. They simply average them together because they think it's just one field and doesn't matter. Another thing is what cable you use. If you use high frequency, which you typically can't with projector, but you can with LCD TVs, it's perfect. If you use composite cable, it's okay. If you use S-Video, depends. Some work, some not. If you use something high-tech like WebXE and RGB monitor, it doesn't work. If you use emulator with best possible image settings, it doesn't work. If you use the most correct emulation, it does work. So
basically,
really depends.
What do you optimize this for?
I optimize this for nice image and I adjust the hardware so it works.
All right.
And typically it's not a big problem. So it's the original picture. Of course, the main difference besides smoothness and details is the same resolution as this 160 by 100, is the fact that the image is darker because every second line is basically black. But especially on CRTs, it's something you won't really notice because you are expecting black lines on CRTs. This is another nice picture, this is the first mode with 16 colors. This is 24 colors, not much improvement, but certainly better in some areas. This is 25/6 colors, and this is the best one, which is 88 colors, and which typically on CRT looks almost perfect, because on most CRTs the individual pixels, even if it's low res pixels, are really not very visible. So if you go, you can really see it improving. It's interesting that the reflection in the window on this picture looks quite okay, even on the worst. And it doesn't change much. But for example, the color, it's not even brightness yet, it's just changed from green to red. it's improved with every iteration a lot. And again, original picture. It's another picture. It's just mess. The picture has a lot of details in the face, which are just gone. And as you add colors, it gets better and better. And the best one is almost perfect again, especially if you run it on CRT, it's a lot better. Again, original picture. I have some more pictures and some projects which came out of this. Even one is, I will show it here. One is what I call Pong, which is basically mode I wasn't talking about today because it only uses 5 brightnesses. It's not the latest idea I had, but it doesn't use PMG, so I can use PMG for the ball. And its idea to have game like this. It uses character mode, so I can simply draw and quickly draw its one frame rendering. I can even control it something like Arcanoid, but the ball will not go down. So this is basically 20 colors without flickering, because when you move with the picture, it's really hard to combine it with flickering. It will always look bad. I tried many things and no joy, but it's not a picture program, it's basically a game, and the picture is just decoration, so it doesn't have to be perfect. It could be a lot better, but it looks okay. And the kernel code for this code is the most complicated timing I have ever written on Atari, because it uses its character mode, it uses smooth scrolling, so the code which changes the color has to be different based on at what position it's scrolled. So there is a piece of code in the beginning, and there is jump, which depends on if I'm starting on fourth line of the character, I just jump to the code which solves the 4th line. Then there is huge 20 kilobytes of code which creates dual image, because I can't make a loop, that would be too expensive. And then in the end there is another piece of code which depends on what position it's on. So it's really crazy, and there's like 2 cycles headroom. Really is crazy. Maybe there will be one day game like this. Not anytime soon, anyway. And there's another thing I used based on this approach, which were images for Poison's demo Prodigy, very famous after forever. Anyway, this uses something slightly different. It doesn't use the black and white lines, it doesn't use palm mixing, because he wanted something which will run everywhere and look somewhat good. But it's basically just black and white photograph convert to 6 colors, using my trick with inversion and PNG to get 6 brightnesses. And then the palette is changed a bit, so it looks like somewhat color image. But on some pictures it looks really good, but it's basically just 6 color and dithering. And I will show some more images now. They are all only in the best quality possible. This is image I used for when I had to display it on Atari, and I already had the code which worked on PC. This is really good because I know, yes, there is just red in here, there is just yellow here, there is just purple here. So if I had some errors in my code, and I could immediately see what the errors were, and I converted it a lot. You can see again, here are some small, not really big errors. Like on this character, you can see the blocks, which basically means I couldn't use all the colors I wanted. This is another nice picture. This is very nice picture because it looks good almost in any mode. It's basically just a few shades of red, and even in the simplest mode it looks quite okay. This picture I use because on these diagonal lines you can see a lot of squares, maybe not on the projector, but it's one of the pictures which converts really bad because all the limitations, there is a lot of bright and dark close together on diagonal line, which is the worst. And even so, it's quite okay and most people won't notice. This picture has tons of details which just hide every error, so it looks good. There are some other pictures. This is from movie Coco. This is a picture I want to use. I want to make some music disc with covers from game Nier Automata. And this is a picture from the game I want to use for the while the music plays, basically. I also tried some like anime pictures, which are not very good for modes like this, because it has a lot of contrast between pixels. Here, the bright pixels are basically just the eyes. Most of this picture is the average brightness, and dark is here. But magically it perfectly matches with character borders, so there is no visible artifact. This is, of course, picture from my favorite Puyo Puyo. And this is another picture which shouldn't really work in mode like this because it uses a lot of contrast, but somehow it works. There are some errors on this line, but again, nothing really visible. And also I had some idea to make Mandelbrot program for Atari, which would take like hours to compute, but I was trying if there is some way to display the Mandelbrot set like in some nice way on Atari, and this is like the best I could come up with. But those are just simply converted images. I will show you the conversion in the process. And that will be basically everything. The program is just in code. There is no graphical interface for it. No, so it's only usable for me at the moment, and who knows if ever it will be for somebody else. And basically, if I run it, if I find the right key, you can see how oh, maybe not really, because the projector is not really good. You could see how the pixels are slowly developing, and sometimes pixel is moved left, pixel is moved right, and it's the process of the algorithm. I basically take random pixels, computer error in the area, find the better pixel for the position and change it, and this I do again. This is really good because it doesn't create any regular artifact. Everything is just random. And if there is some way of the pixels, or how the pixels can be arranged, if some of the way is better, it will find a solution. So this picture here is basically the current error. Basically, all the colors on Atari are not strong enough. So where there is red, I can do it as much red as was the original picture. So the error in the red area will always be blue. Error in blue area will always be red. That's just how this method works. But even here you can see how during developing of the picture I can use something with less colors, so it's more visible. I can disable this. can see how it's improving and moving closer to gray, I would say. And after it compiles the program and runs it, so I can immediately see how it looks on Atari. I also do some small tricks, like I have pictures like this, which are taken from the emulator, and theoretically you could use photo of your screen, and basically I can use colors taken from the photo, so I don't use palette, file, or there's a big problem because every Atari shows colors slightly different, every emulator shows colors slightly different, so I can measure how different the colors are shown. I basically can create test image, take picture of the result, and then use this image back and use the dithering to match this. It's like a system to calibrate your device, and the difference is not big, but sometimes it's enough to be noticed. So that's mostly all. If you have some questions, you can ask in Czech, I will translate it, or you can try in English, whatever. Any questions? Not really. So thank you that you have no questions, and see you tomorrow in my next lecture.